Okay, does anyone want to see a homework problem?
Yeah, could you do
2B, yeah. Let's see. Okay. This is fascinating video. Okay. So we got this car, and it starts over here at A. Gets to B after 2 seconds, C after 2 more seconds, back in 2 seconds. So it's 2 seconds, tick, 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 tick. And A and B are 6 meters apart. And B and C are 8 meters apart. And so for part B, we're assuming that the 0 position is at C. So I'm going to just sketch sort of a diagram of the motion. It starts here, goes there in 2 seconds, there in another 2, there in another 2, and does it end back at A? Yeah, ends back where it started. That's 6 meters, 8 meters. This interval takes 2 seconds, 2 seconds, 2 seconds, 2 seconds. Okay, and for part B, we're going to choose the 0 position at C in the positive direction to the left. So the 0 position is here. Positive is this way, which means negative is this way. And now I can write out the position labels. So if you start at 0 and go 8 meters in the positive direction, you're at the point positive 8. And if you start at 8 and go 6 meters more in the positive direction, you're at 14 meters positive. And it doesn't say anything about when the when time equals 0 is, I don't think. When that happens, just make time equals 0 the start of the motion. Okay, so the start of the motion is here, that's 0 seconds. This is 2 seconds. 2 more is 4. 2 more is 6. 2 more is 8. And so now I'll do a table. At time 0 seconds, the position is positive 14. At time 2 seconds, the position is 8. At time 4 seconds, the position is 0. At 6 seconds, the position is 8 meters. And at 8 seconds, the position is 14 meters. Any questions about filling that stuff out? Hopefully you're, sort of picking up that you can always follow the exact same approach to do these things. And I think that's usually beneficial to always do it the same way. It keeps you from making dumb mistakes a lot of times. And now it's just a matter of plotting out these points. We always have position on the vertical axis and time on the horizontal axis. The times are 2, 4, 6, 8, and the positions are 0, +8, +14. The first point is 0, 14, so here. Then 2, 8. Then 4, 0. Then 6, 8. And then 8, 14. Anybody have any questions about that? If we started the stopwatch earlier than that, it would shift this graph to the right along that time axis. If we chose the 0 position to be somewhere to the, I guess, somewhere to the negative side, whatever the negative side is. No, wrong. Somewhere to the positive side, it would shift this down. And if we flip the positive and negative directions, it would flip this shape upside down. Okay, any other homework questions you'd like me to go over? All right. We have talked about velocity now. Well, we talked about position so that we could do this stuff. And last time we talked about velocity. Now we have to talk about what acceleration is. So remember that the first thing I said about velocity was that it measures how quickly the position is changing. The acceleration measures how quickly the velocity is changing. Measures how quickly the velocity is changing. And there's, one thing to notice, you should remember these as kind of synonyms of each other. They mean the exact same thing. Constant velocity, so a velocity that doesn't change, and 0 acceleration mean the exact same thing. Because constant velocity means there's no change in the velocity, and so since acceleration measures how quickly it's changing, that means 0 acceleration. One thing to keep in mind, so really we're doing this one-dimensional stuff as kind of a way to piggyback to doing two-dimensional stuff. In 1D, this is kind of, there aren't too many like really fundamental differences between 1D and 2D motion. But in 1D, acceleration can only mean one thing. So in 1D, acceleration can only mean that the speed is changing. That's because the motion is just along a line in 1D. In 2D, though, we're going to see there's a different thing that it can do. So acceleration, it still can mean the speed is changing. And or, so there's something else that it can mean in 2D. It can mean the object is turning. Since there's no such thing as turning if you're driving, moving along a line, we won't see this yet. So I just want to put that in the back of your mind for later when we get to two-dimensional motion. And as far as interpreting acceleration, remember this. So what does it mean? So I said the only way in 1D that you can have acceleration is if the object is changing speed. So the object can either be speeding up or slowing down. And I think probably if I asked you to guess what acceleration is if an object is speeding up, you would say acceleration is positive if it's speeding up. And if it's slowing down, you would think, okay, acceleration must be negative. And that is a perfectly reasonable guess, but that's not how it works. So I want you to remember this, okay? If the velocity and acceleration have the same sign, then the object is speeding up. So you don't know whether the thing is speeding up or slowing down unless you know the signs of both the acceleration and the velocity. If the velocity and acceleration have opposite signs, then the object is slowing down. If at this instant the velocity is equal to 0 and the acceleration is not equal to 0, well, you can't get any slower than velocity equals 0. That means the object is at rest. So this has to be speeding up. Okay? So from the acceleration alone, you can't tell whether something's speeding up or slowing down. You need to know both of those. The units for acceleration are always length divided by time squared. And that means that the SI units are meters per second squared. Okay, yes?
Was for velocity the units length divided by time?
Yep. And this is just length divided by time squared. When we talked about velocity, the next thing we talked about is how you recognize the sign of the velocity on a position versus time graph. Do you remember what it was that defined the velocity on position versus time graphs? You draw a tangent line to the curve, at the point you want. And then what is it about the tangent line?
What is?
What-
Did you make like a line?
You make that tangent, you draw that tangent line, and then what is it about that tangent line that you draw that tells you the slope of it? So yeah, so velocity is determined by the slope of the tangent line. So we're going to do the same thing with acceleration on a position versus time graph. The acceleration is given by the concavity at the desired point. Okay, so another way to say this is the curvature. But what that means is if at the point you're looking at, the curve is part of a shape like this, that's a positive acceleration. Okay. If at the point you're looking at, the curve is part of a line, and any kind of line is the same answer, that's a constant velocity. And so the acceleration is equal to 0. And then last, if it's part of a curve like this, the acceleration is negative. This is called concave up. And the negative one is called concave down. I don't know what grade I was in, but I remember some math teacher told me concave up is like a cup, concave down is like a frown. So that's still how I remember it now that I'm 51. You also can remember positive or negative because this is like the mouth representing someone's attitude. So this is someone with like a positive attitude, negative attitude. You're on your own for remembering the line part, but the line has no concavity at all, so that's 0 acceleration. Okay, so let's start trying to put some of these pieces together. So first of all, let's say we have a position versus time graph that looks like this. And the first point is here. We'll call that A. The second point is here. I'll call that B. And then the third point is here in between those two, and I'll call that C. And we want to know what are the signs of the accelerations at those points. At A, B, and C. Okay, so at A, the curve there, does it look like part of a concave up or a concave down or a line?
Concave up
Or
or down?
down, right. So at A, it's part of a concave down, and so the acceleration is positive. No, negative. The opposite of what I said. Negative. At B, is that part of a concave up or a concave down?
Okay.
That's concave up, so that's a positive acceleration. And then at C, if you zoom in really close, the closer you get zooming into that point C, the closer that'll start to look like a line. You can just think of that as the point where it switches concavity from one to the other one. at some point, so you can think of it as like this concave down part from A is getting less and less concave until right at the point C, it switches from concave down to concave up. And so at that point, the acceleration is equal to 0. Okay? Now, let's ask another question about this graph. Is the object speeding up, slowing down, or neither at those 3 points? So we'll start with the point A. Well, we already know that the acceleration is negative there. To figure out, and that's not enough, remember, to figure out whether something's speeding up or slowing down. We also need to know the sign of the velocity. So let's draw a tangent line to this point, and it looks something like that. Does that have a positive or negative slope, or 0? That's a positive slope. So we have a positive velocity and a negative acceleration. So is this speeding up or slowing down? If it's speeding up if they're the same, slowing down if they're opposite, so this is slowing down. And another way that you can, I guess you can think of this as a way to check that you're thinking about it right, is notice that if you think of the slopes of all the points as you go from left to right here, you can think that the biggest positive slope would be here. And then that slope is getting closer and closer to horizontal as we get closer to the top, that peak. So right at that peak, the velocity is going to be 0. Okay? And so if something's going from a big absolute value to 0, it's slowing down. So it's just another way to think about that. Okay, what about at B? So we know that at B, the acceleration is positive. Let's draw a tangent line, and it would look something like this. So is the slope there positive or negative? Positive. So we have here a positive velocity and a positive acceleration. So is this speeding up or slowing down? Speeding up. Speeding up, yep. And then the last one is C. So at that point C, a tangent line looks like this. Does that have a positive or negative slope? Negative, yep. So for C, we have a negative velocity, a 0 acceleration. And so if the acceleration is 0, the velocity is constant, meaning that the speed isn't changing. So this is no speed change. Any questions about that? Okay, let's think of another case. And now I'm going to give a position versus time graph. And then we're going to draw an arrow in the direction of the acceleration in the real world, like which way the acceleration would be pointing in the world where the object lives. So here's the position versus time graph. And let's say that's the path of the object. Not the path, that's the position versus time graph of the object. And let's say we're interested in this point here. And for part A, the object is moving along this vertical path, and we're calling the positive direction up, and that means the negative direction is down. Okay, so, and then I guess for part B, it's still going to be moving vertically, but we're going to call the positive direction down and the negative direction up. You can do that. I mean, it's just where you place your positive and negative stickers in the path of this object. And what we want to do is draw arrows in the direction of the velocity and the acceleration. For cases A and B. Okay, so for A, well, first, we have to figure out the sign of the velocity and the acceleration. So I'll start with the velocity. There's a tangent line. Does that have a positive or a negative slope? Negative. So the velocity is negative. And now, what's the concavity? Is this part of a concave up curve or a concave down curve or a line? Yeah, that's right, concave down. So here the acceleration is negative. Okay. Well, I didn't ask whether this is speeding up or slowing down, but in this case, is it speeding up or slowing down? Speeding up because they have the same sign, right? And so now we want to represent this motion in the real world where we've chosen for part A the positive direction up and the negative direction down. The velocity is negative, and so the direction of the velocity is this. Okay? The acceleration is negative, so the acceleration is also in the direction of our negative. Okay? Anybody have any questions about that yet? Okay, so now we're going to assume that this graph actually represented the motion in B, where our positive direction was down and our negative was up. Changing what the positive and negative directions mean doesn't change anything about the meaning in math world, in graph world. Okay, that slope is still negative, and that concavity is still negative. Okay, so we still have a negative velocity and a negative acceleration. But now, in interpreting what that means, we're talking about a vertical motion where the positive was down and the negative was up. And so now, which way, according to this graph, which way is the velocity pointing, up or down? Up. Up, that's right. And which way is the acceleration pointing? Also up, yep. Okay, this is confusing at first, no question. We're going to spend a lot of time doing this kind of stuff in labs to sort of make this make sense. But always remember that there are kind of two things going on. There is the representation in the position versus time graph, and then there's the separate representation in the real world that you do with stickers. Okay? Okay, now we're finally going to get to doing some calculations. The calculations we're going to do are for accelerations that are constant. The accelerations don't change. So this topic is called the constant acceleration equations in 1D. And I want to go back to a couple of these graphs before I do this to kind of make sense out of how this all works together. Let's first go back to this one. What was the acceleration at A, positive or negative?
Negative.
Negative. And what was the acceleration at B?
Positive.
Positive. So is this a constant acceleration? No. If as you go through time the acceleration changes, then it can't be constant acceleration. This one, on the other hand, that could possibly be constant acceleration. We don't know for sure, but we can see that over the whole thing, this is a negative acceleration. We can't really eyeball it and say whether it starts out as -2 and then goes to -4 and -3, but we can at least say that the acceleration is negative over the whole path. The whole thing is part of a concave down curve, okay? And so this one might represent constant acceleration. So the calculations we're going to do could not represent this. They could possibly represent this, okay? So not every motion has constant acceleration. But a lot of important ones do. And the most important one is going to be free fall and projectile motion. We're going to see that in the case where there's not too much air resistance, free fall and projectile motion are constant acceleration motions. And so to introduce these equations, I have to introduce a few different variable meanings. So here are the variables we're going to use. So let P sub I and V sub I be the position and velocity when time is equal to 0. And let P sub F and V sub F be the position and velocity when time is time final. And you can think of this as when you click the stopwatch off to look at the time, okay? So this is when you turn the stopwatch off. And so for all of these things, we're only going to be dealing with two different instants in time. The instant that we turn on the stopwatch and then the instant that we click the stopwatch off to look at what the time is, okay? And we don't have any acceleration initial or acceleration final. The reason for that is that acceleration is constant, so all we have is a, you know? And so the three equations for constant acceleration motion are: first, v sub final is equal to v initial plus a times time final. The second one says p sub f is equal to p sub I plus v sub I times time final plus 1/2 times a times time final squared. And then the last one says 2 times a times the quantity p final minus p initial is equal to v final squared minus v initial squared. So these are the three constant acceleration equations. And we're going to see when we go to 2D later that these look the things you use in 2D look very familiar. They look like this with some modifications made to make it work for 2 dimensions. Okay, so now I'm going to give just a general step for calculating things using these equations, and then we'll just go through a bunch of examples. So here are the general steps. So first, in the real world, we're going to choose 4 things. We're going to choose the location that we're going to call p equals 0. That's just our reference location. We're going to imagine sticking a sticker there to measure everything from. We're going to choose a positive direction, which also has the effect of choosing the negative direction as the opposite. So for these, you can think of placing stickers. And then the other 2 things we're going to choose are 2 instants in time when we turn the stopwatch on and then when we click the stopwatch off. So we're going to choose an instant where time is equal to 0. That's where we turn the stopwatch on. And we're going to choose an instant, instant time final. And that's when we're going to turn the stopwatch off. And when we turn the stopwatch off, it says some number of seconds, 8 seconds or 9.6 seconds or something. Okay, once we've chosen these things, now we can list the variables that we know and the variable that we're trying to find out of the complete list. And there's only 6 total variables that we have to consider. So we can always just go down the list and say, like, do we know this one, this one, this one? And so this list of all the variables is time final, acceleration, P initial, P final, V initial, and V final. Third, once we've gone through that list and figured out which ones of those we know and which one we're trying to find, we're going to look for a constant acceleration equation that has the wanted variable and every other variable in the equation is known. If you find that equation, then you can use that equation to solve for what you want, and you're done. Okay? So the reason that this is a requirement for the equation is that with a single equation, you can only solve for one variable. So you want to be able to solve for the variable you're looking for, and in order to do that, everything else in the equation has to be known. There are some cases where, so I'm going to make number 4, I'm going to put it in parentheses. If you're lucky, you won't have to do this, but sometimes you will. So sometimes none of those 3 equations work. And so in that case, use an equation to solve for either time final or acceleration, and then go back to step 2. Okay, and try again. Okay, so those are the 4 steps. They don't make too much sense until you see them used in practice. So now I'm just going to go through a bunch of equations, a bunch of example problems, and try to be clear as I go about each step. Okay, and what you really want to do as you're working on problems is you just want to keep being systematic, go through the same approach every time you do it, and it'll cut down on the number of mistakes you make, and it'll just make it make sense a lot quicker. Okay, so first example. So let's say that a car is traveling at 40 meters per second and it hits the brakes. Can anyone sort of estimate how many miles per hour 40 meters per second is? So I said last time that it's about 2.25 miles per hour for every meter per second. So this is really fast. This is like 90 miles an hour. Okay. And the car stops 30 meters away. Is that too high? Let me see. That's way too high. So it would really take a lot longer than that. So let's say the car stops, let's say 60 meters away. And we want to know 2 things. what's the car's acceleration? And second, how long in time does it take for the car to stop? Okay. All right, well, I'm going to go through these two, and I think this is always the way to do it. Just do it piece by piece as if you're kind of starting over at the second piece. So we're going to do A without thinking about B, okay? All right, well, here is a drawing of what's going on. So here are the 2 points. At this point, the car has a speed of 40 meters per second. Here, the car has come to rest, so the speed is 0 meters per second. And we know that the distance between these is 60 meters. So that's what we're given. And so the first step that I said to do is to choose a position equals 0 and a positive direction. And then an instant for time equals 0 and an instant, so an instant to turn the stopwatch on and an instant to turn the stopwatch off. My 0 position, you can choose whatever point you want, but I think most people would probably choose the 0 position to be where the car is when it starts braking. And then the positive, might as well just make that in the direction of motion, so negative then is the other way. Okay. And so if 0 is at that first point on the left, and if you go 60 meters in the positive direction from the 0, what's the position at this point? So if you start at 0 and go 60 meters in the positive direction, what do you get here?
60 meters?
Yep, positive 60 meters. So that's like the stuff we were doing before. And now the stopwatch. So this is kind of an interesting thing. No matter where you choose your position equals 0 and which direction you choose is positive, you can still do these problems. The answers change a little bit, but those answers will still be right. And when you interpret them into the words of the problem, the answers will agree with each other. But usually you have to make the correct choices of when to turn the stopwatch on and off to do a problem. And to choose when to turn the stopwatch on and off, you want to choose instance where you're given information and instance where you're trying to find information. Okay? And so the two here that we want to use are the start of the acceleration, because we know the speed there and we know a distance from there. So that's going to be at the start of the acceleration. And then the other place where we know or want to find stuff is when it comes to rest. And the time final is always the later instant than the time equals 0, just like a regular, we don't have a negative stopwatch, quantum mechanics stopwatch or something. Okay, so these are our choices, and now based on this, we can start to figure out what variables we know and what we want. And I'm going to list out the variables, all the variables in order, so we can just go through the list. So time final, acceleration, P initial, P final, V initial, V final. Okay, first, do we know how long it takes? So time final. Do we know what the stopwatch says when we click it off? No, we don't know that. For part B, we're going to want to know that, but for now, we're not worried about it. So I'm not going to write that under want, and I'm not going to write that under no. Do we know the acceleration? No, that's what we're trying to find for part A. And I'll cross these off as we go. Do we know the position when we click the stopwatch on? Yes, we do know that. So that's at this instant, this dot here. And that is what we chose as our 0 position. Okay, so PI is equal to 0 meters. And by the way, P initial will always be 0 if you choose your 0 position to be at the start of the motion. Okay, so that's always something you can do if you want. It's not always necessarily the simplest choice to make, but you can always do that. Do we know the position when the car comes to rest at time final? Yeah, we already figured out that's positive 60. Okay, do we know the velocity at time equals 0 when we turn the stopwatch on? We know the speed, and in order to get the velocity, we just have to take the speed and then give it the sign that associated with the direction it's moving. So this is going to be either positive or negative 40. Which one is it in this case? Positive, yep. So the velocity initial is, I'm going to write the positive explicitly. You don't really have to do that, but I'm going to. So 40 meters per second. And then the last one is when we click the stopwatch off, do we know what the car's velocity is? What is it? 0, yep. Okay, so now we're going to look at the 3. We know we're done with this whole list, so we know we're done with this step. And we're going to look at the 3 constant acceleration equations and try to find one that has A in it, because that's what we want, and everything else in it is listed here. Okay, so let's just, for the first one, let's just go through the equations one by one and just check them out. You can always just guess at one and just check out if it works. So, okay, let's try the first one. I guess I'll write them down. So the first one says V final is equal to V initial plus A times TF. Yeah, right. But don't ruin the surprise for people. Just kidding. So let's try this one. We know V final. Oh, well, let's start with, it definitely has to have the variable that we're looking for. It does have A, so that's a good start for this one. Next, does it have V final? Yes. V initial is known. T final, that's the problem with this one, right? We don't know T final, and so we can't use this. So now we'll go to the second one that says P final is equal to P initial plus V initial time final plus 1/2 A TF squared. And you can see already you have the same problem here. There's a T final and we don't know it. So now let's go to the third one. Now we're really hoping it's the third one, or else we're going to have to do all these extra steps. So the third one says 2 times A times the quantity P final minus P initial is equal to V final squared minus V initial squared. Okay, does this equation have A in it? Yes, so that's a good start. And now we'll go through the other variables in the equation. PF, we know. PI, we know. VF, we know. VI, we know. And so this one should work. And so now we'll just plug in all these values. So 2 times A, the thing we're trying to find, times the quantity PF minus PI. PF is 60 meters. I'm just going to tell you, I'm not going to make you do this, but if you were really careful and kept all the units in this and multiplied out units and canceled them when they canceled and everything, the answer that you get from this equation would give you the correct units for what you're trying to calculate. And so it is nice to know that that's possible, but it makes it a lot more complicated. And so I'm just going to do these with numbers, and then I'm just going to give the correct units for the thing I'm trying to solve for at the end. Okay, so this is 60 minus P initial is 0. And that's equal to 0 squared minus 40 squared. Multiply out the left side and you get 120A is equal to negative 1600. Right away you can divide both by 10, say. You get negative 12A is equal to negative 160. So that is, I think that says A is equal to negative 13.3. Repeating.
Question. Why
Yep.
not directly just divide by 120?
Yeah, just do that, yeah. But I don't have I didn't set a calculator out here. So, yeah, can someone check that and make sure that's right? I don't know if, I think it is.
It is.
Okay. You know what helps with doing arithmetic in your head is sitting up here doing arithmetic in your head for 16 years. I have found that. Okay, so the acceleration is negative 13.3. And now there's one sort of mental sanity check you can do. Is this car speeding up or slowing down? Slowing down. The velocity over its whole motion is positive, right? And so for it to be slowing down with a positive velocity, we know that the acceleration has to be negative. That's what's required for something to be slowing down. And so that's a good sign that we got a negative value for the acceleration. Okay? So now we'll go on to part B. Now we're trying to figure out what time final is, what the stopwatch says when it stops. Okay. The first question is there any reason to change any of our 4 choices? And really the only reason that you would ever have to change your 4 choices of position equals 0, positive direction, time equals 0, and time final is if you're trying to calculate something at a different instant than one of those 2 that you chose for time equals 0 and time final. Okay? We're not looking for a value at a new instant. So we might as well just keep all of these things the same. We're just going to keep the same position equals 0, positive direction, time equals 0 instant, and time final instant. And the nice thing, if you keep all 4 of these things the same, the nice thing you have going for you is everything that you knew before is still true. You haven't changed the meanings of any of these variables. If you change any of these, that's not true. And you'll have to go through listing things out all over again. So when you keep those the same, the list of variables doesn't change. Okay, so I'm going to list out what we know and what we want. And so I'm just going to go up to this list and take all the stuff we know. And we actually know one more thing now. We know the acceleration. So PI is equal to 0. PF is equal to 60. Is that what it was, 60? VI is equal to 40. VF is equal to 0. And now we know that the acceleration is equal to negative 13.3 repeating. And what are we looking for now? What are we trying to find?
Time final.
Yep, time final, TF. Okay, so we're looking for an equation that works. Let's try this one. VF is equal to VI plus ATF. This has TF in it, so that's a good start. Then VF we know, VI we know, and A we know. So this will work. It turns out that for this one, the second equation will work too. But if you ever have the chance to use that first simplest equation, use that. There's no squares in it. You're not going to have to worry about, remember when you take plus or minus, when you take the square root of a variable, you have to worry about whether it's plus or minus and stuff. This you don't have to worry about. So whenever you can use that, do it. Okay, so we got 0 is equal to 40 plus negative 13.3 repeating TF. And so 13.3 repeating TF is equal to 40. And so TF is equal to 3 seconds, I think.
Why is it 13.3 repeat?
That is the acceleration that we got from above.
I understand, but why is it repeating? Why doesn't it have a line on the feet? What does that mean?
Oh, that just means it's really 13.3333333 forever. So that's just a short way of writing it. Or, you know, like I said, I don't really care how you round off. So if you just want to call that 13.33 or something, that's fine. It'll change the answer a little, but not much. Any other questions about that? Okay. How much time do we have? Let's do one more. Okay, so let's say that we have a ball rolling down a ramp. And let's say that at this location A, it has a speed of 2 meters per second. And then at this point B, it has a speed of 5 meters per second. And let's say that the distance between these is that how I want to do it? Let's say that the elapsed time to get from A to B is 1.0 second. And we want to calculate the distance between those 2 points. Okay. So here's what we care about. Here's the point A, here's the point B. We know that at the point A, the speed is 2 meters per second. At the point B, it's 5 meters per second. And now we have to make our 4 choices: position equals 0, positive direction, and when to turn on and turn off the stopwatch. Might as well make that point A our 0 position, although it doesn't change the problem if you choose a different one. And then might as well choose the positive direction to be down the ramp. Negative is this way. Oh, I just realized 3, maybe that'll be all right. Okay. So here's the choices of positive direction and negative. And now, what do we want to choose as our instance when we turn the stopwatch on and off? So when do we want to click the stopwatch on? Remember, that's based on where we have information and where we're looking for information.
Wouldn't it be point A?
Yeah, so this is going to be when it passes point A. And then when do we want to click the stopwatch off?
B?
Yep, passes B. And now we can list out what we know and what we want. I'm going to make a list of all the variables again. So TF, A, P initial, P final, V initial, V final. And then what we know and want. So the first one is T final. Do we know what the stopwatch says when we click it off? Yes, that is equal to 1. Do we know the acceleration? No, we're not looking for that though, so I'll leave it off for now. Do we know the initial position? The position when we click the stopwatch on?
Yes.
Yep, that's what we chose to be our 0, so that's 0 meters. Do we know the position when we click the stopwatch off? No, but that's the key to answering the question. And so this is the thing we're looking for, P final. Yep,
How do we know that the time final is 1 second?
that was given.
Oh, okay.
The elapsed time is 1 second. Okay, do we know the velocity when we turn the stopwatch on? Yep. So we know that that's 2 meters per second, and then you have to think about the direction it's moving. This is moving in our positive direction, so this is going to be positive 2 meters per second. And then V final, the speed is 5 meters per second. It's still going to be moving in the positive direction, so that's positive 5. Okay, is there an equation that has P final in it and everything else in it is in this list? And the answer is none of them work, and the reason is that all 3 of those equations have acceleration in it, and we don't know acceleration. Okay, and so now we go to, so no equation works. So then you can be sad for a little while, but then you have to pick yourself back up and say like, okay, now we're going to calculate the acceleration. So we'll forget about this for a second, and the thing we want is going to be the acceleration. Okay, so now go through the 3 equations and see if there's one that has acceleration in it and everything else in it is listed here. So let's try this one. VF is equal to VI plus ATF. This one has acceleration. V final we know, V initial we know, TF we know, so this one works. So we're going to use this to find A. So 5 is equal to 2 plus 1 times A. And so 3 is equal to A. Well, so there it is. A is equal to 3 meters per second squared. And now we can put, now A is also known, and we can go back to trying to find PF. Okay. So now we're going back to finding PF. Okay, so the first equation, does this one work?
No.
It does not work because it doesn't have PF in it, so you can't solve for something that's not in the equation. How about this one? PF is equal to PI plus VITF plus 1/2 ATF squared.
Yes.
This one works, yep. So PF is equal to 0 plus 2 times 1 plus 1/2 times 3 times 1 squared. And so PF is equal to 2 plus 1.5, so 3.5 meters. So the points A and B are 3.5 meters apart. Any questions about that? Okay, well, that's it for today, and I'll give you a few problems like this to try to work through. And on Tuesday, feel free to bring questions if there are ones you want me to go through. I'm happy to do that. But remember, there's also solutions available if you get stuck. So look at those if you need a hint as you try to work through these. And little by little, we're just going to get used to this process.